We present CADTalk, an algorithm and benchmark for semantic commenting of CAD programs. Computer-aided design, CAD for short, is the industry standard for representing 3D shapes as sequences of geometric instructions, also referred to as CAD programs. Popular systems like Fusion 360 and SketchUp are developed for CAD program creation, execution, and even for generation. CAD programs are compact, expressive, and parametric. See here the bike and motorbike programs, which are highly structured and well-written. Let's take a deep look at the bike program. It's highly modular, with each semantic part written as a function. Inside the frame module, it has top tube, seat, etc. More modules are included, like the fork, the handlebar, and the saddle, to form the whole bike. Pay attention to the hyperparameters. For example, you can change the number of spokes, the wheel diameters, and the frame height to obtain a very different bike easily. As you can see, readable semantics and good parameterization helps the content creation. However, not all CAD programs are well organized and semantically commented. Look at this program of the lovely bird. Is almost unreadable, let alone edit and reuse of parts. Besides, recent efforts on shape program generation only consider geometry. The lack of semantics prevents the understanding, editing, and reusing of the CAD programs in many applications. So, in this work, we have proposed a new problem, that is semantic commenting of CAD programs. The input is a plain CAD program. We assume that the executor is accessible, thus producing the corresponding 3D shape. Given the input, the goal is to analyze the program and augment it with semantic comments, like the train with different parts and semantic meanings. How can we achieve it? Intuitively, we may think of solving this problem solely in the program domain. However, it's challenging, and there is no large dataset of commented CAD program that could be used to train language-specific models. Fortunately, with the help of the executor, we can access the corresponding visual domain, where the semantic analysis is much easier and tractable. We thus cast the problem of program semantic commenting into a problem of image semantic experimentation. However, there are a few challenges working on the visual domain. Firstly, the programs, especially human-made programs, have complex structures with control flows and subroutines. Thus, the propagation of the resulting label from the visual domain to the program domain is non-trivial. A program parsing step is demanded to find out where to put comments and register the commentable code blocks with image pixels to bridge the two domains. Secondly, the CAD programs usually come without any material textures, leading to textless images that challenge the vision models. Also, the programs are sometimes flat and abstracted, like the airplane, which could raise big problems for vision models as well. To solve it, an image-to-image translation step with ControlNet is designed to translate the CG-style image into photorealistic images that better benefits from foundational vision models. Thirdly, CAD programs encode various shapes across arbitrary categories like the animal, daily objects, etc. Thus, open vocabulary labels from large language models and open vocabulary semantic segmentation from foundational vision models are required. With all the mentioned ingredients, we have designed our algorithm to solve the program semantic commenting problem. Let's go through each step one by one. Firstly, program parsing. Given a program, we first convert it into its corresponding abstracted syntax tree with the parsing toolkit. We then traverse the syntax tree from the top down using the breadth-first search until we reach an irreducible block. The irreducible block is a sequence of instructions that corresponds either to a single geometric primitive like cuboid, ellipsoid, etc., or to a difference, interaction, or Hall operations on primitives. Here, the red color highlights two such blocks corresponding to the beak and the wing structure. We label the irreducible block as commentable leaf nodes and traverse the tree upwards to collect all the commentable blocks as node parents or commentable nodes. Here, the left wing and the tail corresponding to the W and the T nodes separately. The parsing step also gives us the pixel and commentable code block correspondence, which serve as the bridges for later steps. In a second step, we use ControlNet to translate images. Specifically, we execute the program to obtain the shape and select 10 views around the shape to render its depth map. The depth map along with the text input are passed to ControlNet to generate realistic images. Note, for each view, we generate 4 realistic images to improve the robustness. In our scenario, the view consistency is not necessary, while we observe that diversity in appearance helps to recognize parts. Thence, object parts that might be ambiguous and a specific appearance might become recognizable and different appearance. The third step is semantically segment images. Specifically, given the shape category, we resort to ChatGPT for a list of possible part semantics and then fed them as the prompt for the open vocabulary detection algorithm, like Dino here, to produce a per part bounding boxes, and also exploit SAM to further produce a dense pixel segmentation within each bounding box. Here, there are two more examples better demonstrating the detection and segmentation results. Each bounding box gets a confidence score along with the segmentation mask. Finally, the last step is cross-view, cross-image voting. We employ the score-based voting across all 10 views and per view 4 image instances. The Dino confidence score and the SAM semantic mask are aggregated in the score calculation. Remember that we have built the code block and pixel correspondence in the parsing step, thus the voted label can be transferred back to the program successfully. To evaluate our algorithm and build the test bed for future research, we have contributed CADTalk, a new dataset for program semantic commenting. The dataset contains 2 sources. The first is the human-made programs, as like the by here. Such programs are usually complex with defined blocks and flows, and it exhibits a large diversity of instructions and program constructs, which can be difficult to reason about in the program domain. The second source is machine-made programs like the dog and desk here. Such programs are usually simple with fewer instructions and flat structure without meaningful code blocks, and they are usually abstracted, reading problem to reason about in the visual domain. The abstraction level can be controlled by tuning hyperparameters, exhibiting large variation. We have selected the airplane, chair, table, and animal categories for machine-made programs. A visual example of the dataset is shown here. The 3 font models are colored using program labels from the ground truth. Check out our paper from detailed dataset statistics. We then evaluate our method on the benchmark with 2 metrics, the block accuracy and the semantic IOU. For both metrics, the higher the better. The block accuracy quantifies the general performance, while the semantic IOU considers the label distribution among blocks, making it sensitive to the long tail problem, where some labels only cover a few blocks. Our statistical performance is reported here. We have built the first baseline for this new problem on the benchmark dataset. The numbers overall are good. We are waiting for more future research to compare against us. Also, the human-made programs are reasonably harder than the machine-made programs. To better understand the importance of technical modules of our method, we have designed a few ablation studies by removing the interesting modules. Here, we remove the multi-view generation, the ControlNet image translation, and the SAM dense segmentation respectively. From the statistics, compared with the before method, the performance drops quite a lot if either ControlNet or SAM are omitted. It's only about 20 to 30. While removing multi-view images causes notable degradation, but not that much. We have compared our method against 2 SOTAM approaches. The first one is Parsley for zero-shot point cloud segmentation. As you can see, they also adopted a foundational vision model to do image space part segmentation and voted back to the point cloud. A visual comparison is shown here. Mislabeled parts can be seen from their results. We hypothesize that the poor performance is because Parsley relies on traditional rendering of point cloud to perform visual reasoning, which results in non-released images in our context. See our paper and supplementary for statistical result and more analysis. The second work is SOTA for zero-shot segmentation. Similarly, GLIP is used for multi-view image part segmentation followed by a voting step. We conducted a comparison. The visual results show that the segmentations are competitive on the realistic house, but SOTA struggle on the more abstracted Moai sculpture and fails on the abstracted airplane. The reason is that the gap between the rendered image from abstracted shape and the photographs used for training the large image language models, while ControlNet in our pipeline solved this problem effectively. Our method can comment on programs generated by shapcoder. After pre-processing, we successfully comment on code blocks with correct semantics. One interesting observation is that shapcoder abstraction might across semantic parts. For example, in the right data point, the ABS20 function includes both the seat and part of the back. This might suggest an inspiring future direction to consider semantics when abstracting the shape. As we have introduced, the program commenting task can be solved solely at the program domain, although it's challenging. We have experimented ChatGPT-4 to comment on a program, give another program with comments as an example. The right part illustrates such a prototype, where we input the instruction, the example, and the desired task, and ChatGPT outputs a commented program. To better understand its ability, we have designed 5 different experimental settings. Option A is purely zero-shot prediction without examples provided. Option B is one-shot prediction, but the example is incomplete. Option C is one-shot prediction. The example is complete, but made of different primitives. Option D is one-shot prediction. The example is complete and made of the same cuboid primitives. Option E is one-shot prediction. The example is complete, but comes from a different category. Visual results are shown here. The experiment revealed that, to our surprise, in option D, a single example is enough for ChatGPT to successfully comment programs that represent the same object category with the same geometric primitives. When asked to explain its answer, ChatGPT reported using the volume and relative position of the parts as evidence, such as the fact that the body should have the biggest volume, while the wings should be attached on the 2 sides of the body. However, the other configuration B, C, and E revealed that these spatial reasoning skills does not extend to the examples that are incomplete of another category or made of different primitives. Check the paper and supplementary material for more details. Our method is not perfect. There are some failure cases. First of all, we inherit drawbacks from ControlNet. In this example, the small details of the scalp tassels are not generated in the realistic image from ControlNet. We thus mislabel it in the program, even though geometrically it's clear. Second, given a turkey depth map, ControlNet generates an unexpected image because we think it confused the bird turkey with the country turkey. Third, Dino wrongly predicts the broom to the head, but we cannot correct it. There are also a few limitations. For example, we cannot reorder or restruct the program if it's badly written and the code block semantics are not clear. Second, we cannot comment on instruction that remove geometry. See the window of the trim. It does not produce any pixel, thus cannot recognized by vision models. A potential solution is to render the removed geometry. Third, the current CADTalk real data track only contains 45 programs, which is too little to serve as training data. For future work, there are many inspiring directions to explore. First, For visual semantic analysis, multimodality inputs like the program, the 3D shape, and the 2D renderings can be exploited together. Second, we plan to assign meaningful labels to program parameters, and reason about differences by vision models can be a promising solution. To conclude, we have proposed a new problem, a new benchmark dataset, and a novel solution. We hope that more and more research can be conducted on this problem. The code is open sourced on GitHub, and more details are presented on our project page. Welcome to check it out and have a try. Thanks for watching.